Okay, so shall we start?
Let's give folks a couple of minutes because they might be jumping around the meeting. I invited Michael Parker for this meeting. It was really amazing to see the things moving forward and the purpose. And there are lots of other folks in this room who are working on the teleological and the purpose. And I thought it will be very exciting. Now I hand over to the Eduardo.
Okay, so hello everyone and welcome to today's webinar hosted as part of the International Conference on Thermodynamics 2.0. It is really a pleasure to have such a distinguished and diverse audience joining us today. Thermodynamics 2.0 is more than just a conference. It's a platform for scientific evolution where the natural sciences and social sciences intersect. We challenge conventional boundaries to explore new paradigms. For me, it's really a honor to introduce today's speaker, Michael Parker. Dr. Parker is a research fellow at the School of Computer Science and Electronic Engineering at the University Essex, and a pioneer thinker in applying thermodynamic principles to computation and communication theory. Among his many contributions, he has introduced the first absolute energy efficiency metric for ICT technologies, discovered the fundamental principles of quantitative geometrical thermodynamics, and applied these insights to fields ranging from subatomic physics to the mathematical foundations of purpose. With over than 170 peer-reviewed publications, more than 20 patents, and significant contribution to fields such as photonic communications, quantum cryptography, and 5G, 6G network, Dr. Parker's work exemplifies the interdisciplinary spirit of the Thermodynamics Conference. Please join me in welcome Dr. Michael Parker. So, Dr. Parker, the floor is yours.
So, thank you for the opportunity and this invitation to speak to such a distinguished set of people from the Thermodynamics 2.0 series. I seem to have a lot of overlap in our interests and approach to thermodynamics. Indeed, this is I received the invitation from RAM based on a paper that I published only a few weeks ago with my colleagues, Professors Chris Jeans and also Professor Stuart Walker from the University of Essex, in the journal Entropy, based on called a metric for the entropic purpose of a system. And with them, I've been actually investigating the fundamentals of thermodynamics and information theory for some decades now, actually for quite a long time, and we've made some remarkable progress, let's say, and I'm quite excited to talk to you on our latest recent work investigating the entropic purpose of a system using thermodynamics. So we have here a cartoon from our paper with Aristotle, Clausius, and Shannon having a discussion around the table, with Aristotle asking about Nautilus's purpose. This is the circular spiral sea creature. Clausius asking how much works in his coal, and Shannon what's the information for. And these are all issues of purpose. And these are, of course, Clausius and Shannon founding fathers of thermodynamics, entropy, and information theory, and Aristotle very much associated with the ancient Greeks and issues of causality and purpose from his perspective. And it's interesting that we've been able to discover a way to address the issue of purpose, but from a very scientific perspective, and that's somewhat unexpected in the sense that modern science for the last few centuries has made fantastic progress, remarkable strides, but one of the first things they had to do was to put aside the basic precepts of Aristotle and remove issues of teleology that Aristotle was introducing, and modern science, physics, has been able to achieve considerable success using the methods of modern science. So it's somewhat interesting that we feel confident enough now to perhaps start bringing back into science concepts that most people would have thought was impossible in science, such as purpose. Now we're looking at it something like a pared down version, which we call entropic purpose. Let me just get to the next slide. So purpose is quite ubiquitous actually in the universe, or in the living world. So perhaps that's only, as far as we know, only bound on our own planet Earth. But for things which have are animate and have life, purpose is ubiquitous. And as Raymond and Dennis Noble have recently written in a book that they've published last year, agency and purposeful action is a defining property of all living systems. But the issue of purpose has never been quite quantified from a scientific perspective, in issues of origin of life and consciousness. These are kind of very huge topics. Purpose and agency is important, but there are actually also quite useful engineering applications for, if you can define purpose, in artificial life and AI and cybersecurity, where there are advantages if you can distinguish between bots and real people. As in, when there's bad behaviour or bad actors, you need to understand that their purpose will often reveal what the actions, or be able to distinguish between a bad actor and a good actor, or even need potentially between a bot and a real person. So being able to study purpose in a scientific fashion actually had a lot of interest, both practical as well as more philosophical. And what we've done is to use the Shannon information. Now, when Shannon introduced his metric for information based on entropy in 1948, his innovation was that he was able to create a metric or measure information in an impersonal, objective, scientific fashion. So up to then, information would have been full as this is what one person knows and another person doesn't know. But he was able to introduce Shannon entropy or Shannon information using his impersonal metric, and we're in a sense we're building on that in defining entropic purpose as the same kind of impersonal way of defining purpose, in a way that is impersonal and scientific and objective. But being able to do that has required some quite interesting conceptual innovations, and it's quite mathematical, just as Shannon theory is quite mathematical. But we've been able to find, first of all, that by introducing complex time, real and imaginary thermodynamic time, that gives us an extra degree of freedom to be able to start defining purpose. And then we've been working on a field which we call quantitative geometric thermodynamics, QGT, for some years now. And it's a very powerful mathematical framework based basically on Lagrangian and Hamiltonian, but in a thermodynamic sense. And we've been able to define within this framework and complex time what we call a purposive Lagrangian. And being able to define such a Lagrangian is incredibly powerful. As in, I'll show later how Lagrangians underpin most of all physics. And once if you can define a Lagrangian, then all sorts of mathematical symmetries, conservation laws, and means of analysis become available to give you a very powerful insight into what's going on. And so it's a very powerful tool. And if we've got it as purpose, then that would be a very powerful idea. Now, one of the underlying assumptions or basic axioms that we're working on is generally the physicists out there tend to think that thermodynamics is an emergent field emerging out of statistical mechanics, whereas what we're finding with our quantitative geometric thermodynamics and the able to definition of a purposive Lagrangian is actually that thermodynamics is as fundamental as kinematics, whereas classical physics, classical kinematics is based on action and the Planck constant, we can define in parallel a completely parallel universe or way of description of the universe, but which is thermodynamics and based on the Boltzmann constant as its fundamental quantum of entropy. And which means that this idea of entropic purpose is actually mathematically and scientifically then very, very powerful. So if we go to the next slide, I just want to discuss a little bit of the thermodynamics of complex time. This innovation of having two-dimensional time or a complex time plane of real time and imaginary time, and by defining time in two dimensions, it solves a lot of paradoxes and conundrums which have beset the physics community. Basically, the two orthogonal times, real time is a time that you associate with irreversible processes which create entropy and are dissipative, whereas imaginary time are for those processes which are reversible, for which the entropy doesn't increase and are thermodynamically reversible and go backwards. And in fact, things like the Schrödinger equation, or indeed all the fundamental equations of quantum mechanics and even general relativity are essentially reversible, and you can't tell if they're running forwards or backwards in time. And this leads to one of the paradoxes. Well, where does the dissipation and the reversibility come from when these fundamental equations are reversible? And in a sense, this is what's known as the Lohr-Schmidt paradox as to how do we get dissipation and well, the second law of thermodynamics in effect. How does that arise out of these equations, quantum mechanics and general relativity, which are essentially reversible in nature, and that's quite a paradox. But by considering time as orthogonal, real and imaginary, the orthogonal time, which you might call which is actually real time mathematically, which is dissipative, we call it the tau time. And what we find is, and we published this in a paper in Entropy a couple of years ago, that if you have the diffusion equation on one hand or the Schrödinger equation on the other, they're exactly the same equation, but one has real time and the other has imaginary time, and that's what the issue is that time has a real and imaginary component, and in effect, what the time that we experience is at each instant in time is the resultant. It's a scalar, but it is the length of that time vector across the complex time plane. So I call that capital T, which looks like a temperature, but it's not. I define it as being our empirical or measured time of a process. And you have any process which has a reversible and irreversible, dissipative or non-dissipative aspects to it, follows a trajectory across the complex time plane, and that's how you build in a unified fashion for any system a means to have both reversibility and irreversibility in that process, and it follows a trajectory across the complex time plane. By defining a complex time plane, we also actually solve in cosmology, in equations of relativity, we have what's called the Minkowski metric, the metric which defines how time and space are related to each other in terms of when you square it, whether it's positive or negative. In cosmology, you have a choice of metric. Either the most common one is -1 minus plus plus plus, which says that time is imaginary and three-dimensional space is real. But the converse is also allowable, which is +1, -1, -1, -1, and they're considered to be equivalent. That there's no actual distinction between these two metrics. You just have to choose your convention as to which metric you choose, and then stick to it, and be consistent. But the choice of which to use in the current thought is just purely convention. Whereas what we understand, that we can see now, is in fact the reason why you have two potential metrics is because what one metric is essentially reversible, non-dissipative, and the other metric is irreversible and dissipative, so they're not equivalent. They define the reversible or irreversible thermodynamical process that's taking place. And in our paper that we published 2 years ago, we also discovered, in a sense, that by defining our complex time, you define the energy is defined by the Hamiltonian, which is what you would see in the Schrödinger equation, for example, and that defines your reversible process. But there's a conjugate quantity, the entropy production, which is basically the rate of change of entropy, which we use a symbol capital Pi, and that operates on the orthogonal time, on the real or dissipative time axis. But these two quantities are actually equivalent. You can show that the Hilbert transform are related to each other, but also Wick rotations, for those who know, kind of the geometric 90-degree rotation, they are equivalent to each other. But one describes the energy characteristic of the system, whereas the entropy production relates to how the entropy changes, or the rate of change of entropy of the system. And this is quite a very powerful unifying approach to understanding any system which has both dissipative and reversible characteristics. So this complex time is a very powerful way of understanding what's going on with real physical processes. So we've got complex time. Just the other innovation, so to speak, that we've discovered in order to create a Lagrangian and Hamiltonian framework is excuse me, someone's trying to phone me. Is to define Shannon information, the Shannon metric, in space-time. Now, what we found is that information has certain characteristics and properties, and in space-time, it basically the point of non-analyticity, a point which cannot be predicted or determined, and it is essentially acausal, and that's the characteristic of information. And you can have a singularity in effect, a point in space-time, which we show by this rho, and which actually was just show it has a kind of inverse square law field. So you've got a point right at the center, if it's like a point mass or point charge or point anything, but it's a point of non-analyticity and creates a field around it, and you and that point of non-analyticity is your basic unit of Shannon information. And when you apply the Shannon metric to it, you find, which is basically that the information due to a point of non-analyticity location at a time t and a point x, to do the calculate its information content, you do a line integral along the time axis. So we make a distinction. This is our convention. That information is defined as the time integral of the Shannon metric of a point of non-analyticity, whereas the entropy is the space integral. So in a sense, just like an optical fiber, you have a lot of information, data coming down a fiber optic, and that's very much in the time domain, whereas space, if it's like for your conventional way of understanding entropy, it's kind of the disorder of the different configurations. That's very much a spatial type quantity, and so you do to calculate entropy, you do a line integral in space. Now, what's interesting is in actually calculating the information or entropy, which using the Shannon metric, rho log rho, where this rho is an inverse square law field, and you do your integral over time or space. The result actually it comes out when it boils down. It is very simple. It's simply the Boltzmann constant, because that's what you introduce to ground in the physical world. But it's simply the logarithm of the space, or the logarithm of the time coordinate of that point of non-analyticity. And what in fact has happened is that a point of non-analyticity in Euclidean space. So this the indicator here is a representation of a point of non-analyticity in Euclidean space. When you calculate its information or entropy, let's say, you find that it becomes logarithmic. And actually what it means is that the information calculating using the Shannon metric to calculate the information of that point of non-analyticity leads you to a hyperbolic space-time description. So that you translate from Euclidean into a hyperbolic space-time, and that hyperbolic space-time gives you what it means is it's imbued with information. If you have a hyperbolic space-time metric, or consider space and time to be hyperbolic in nature, that's intrinsically informational in nature. And this is already work that I published with Stuart Walker some 15 years ago, actually. And what's really quite remarkable is that there's a lot of eminent, well, let's say it's Roger Penrose, a very eminent cosmologist, Nobel Prize winner. His suspicion is that the universe actually does have an overall hyperbolic geometry. That the universe really is hyperbolic in nature, and we have, in his book, the Road to Reality, he's got a nice figure there from Escher print of the angels and the devils, of what a hyperbolic space looks like, and then there's a quite well-known image by Budassi as well of a hyperbolic representation of the universe with the Earth at its center. So this idea of having a hyperbolic space-time is quite recognized, but it goes against our conventional assumption that space-time is Euclidean, but it is but it can be considered to be Euclidean in a small local approximation. So if we just look close to the center and keep our attention close to the center, then everything looks quite nicely Euclidean. But immediately you start expanding your either looking back in time or looking over large areas in space, then that hyperbolic nature will start becoming more apparent. And in fact, this is what we need is hyperbolic. And the point is that when Penrose, Escher, and Budassi have this considered it the hyperbolic nature to space and time, they didn't quite appreciate that actually by doing so you are imbuing a huge amount of information or intrinsic information into that space-time, hyperbolic space-time. It's intrinsically informational. When you realize that space-time is intrinsically informational, then that's a very different way of thinking about our universe, and it's worth that needs to be kept in mind. So and the equation for hyperbolic geometry is logarithmic, and it's quite simple. And this is I apologize for all the mathematics, but I need to show you this mathematics exists. It's true, and it's actually it's not so dissimilar to what is already known. But if you're going to start trying to define a Lagrangian or Hamiltonian, you need two conjugate variables of position and momentum, Q and P, and so we define the hyperbolic position or time as simply the logarithmic of your time. I'm going to stick to time now because looking at entropic purpose, we need time. And Z is just a normalizing factor, which actually we call the holographic radius, but that's come back to that. And it normalizes it. So from a mathematical physical perspective, it's well behaved. It's and then you multiply again by Z again. So it has units of time or space as required. And you can differentiate with respect to the capital T, the measured or empirical time to give a kind of velocity, Q prime, and that's very nicely. You can do the mathematics quite nicely, and that's your velocity, and the inverse of it is what's called the phase velocity. And in fact, momentum then is the P. As we know from our kinematics, is mass times velocity, and we define what we call a thermodynamic or entropic mass, ms, and then multiply by c, speed of light, and the hyperbolic velocity, and that actually has units of velocity. And the thermodynamic mass itself is a purely geometric construct. It's quantized again by Boltzmann constant, so it's nicely thermodynamic. And it's kappa, which is basically a wave number. So we have a length scale, which defines the length scale that we're operating at. And in thermodynamics, in particular with entropy, where everything is logarithmic, basically you operate to a law you might call the relativity of scale. That you have to define what scale you are operating at. And we know that the university operates at multiple scales, but you have to choose your scale. Just like in relativity, you have to define your frame of reference. So also in thermodynamics, or when you're considering entropy or information for that matter, you have to define your length scale, and that's your frame of reference for scale. So we have our P's and Q's. And now what we call the kinetic component, kinetic entropy, is simply the integral of P d q prime, as in, and we have something actually that looks quite similar to like a half mv squared, which is what you would expect in kinematics, but it's also got the logarithm in there, and that logarithm is that characteristic of entropy, thermodynamics, and hyperbolic space as well. And that's the kinetic entropy, and then the potential. You have a potential term as well, potential entropy, V, which depends on space. No derivatives. It can be defined also similarly like MGH for the potential of a gravitational field. It's mass times the position times, and this is actually the hyperbolic acceleration. which looks a little bit different compared to the Euclidean version, but it's still the acceleration. And then you can define the Hamiltonian is simply, or entropic or thermodynamic Hamiltonian is the sum of the kinetic entropy and the potential entropy. So minus a half c log q prime squared and plus vq. And in order to get the Lagrangian, which is what we're interested in, you do what's called a Legendre transform, which is looking at the p and q primes. And this is, you need to have your appropriate phase space for using your p and q conjugates. And this is actually the p and q prime, which is conserved, and that gives you your Lagrangian. So we have here a Lagrangian defined thermodynamically, which is actually different, which is isomorphic, in fact, to the kinematic Lagrangians based on action and the Planck constant. But this is actually all based on the Boltzmann constant and independent. It's an independent formulation of Lagrangians. So and then the paper we wrote and published recently, we just said there exists, we can define our purposive Lagrangian exactly analytically in this term with a kinetic term and a potential term, and having defined Lagrangian, then you can then apply the Euler-Lagrange equation, calculus of variations, to show basically the principle of least purpose in effect. Show that you can put your Lagrangian into this differential equation, which is quite complicated in a way, but it's fundamental. It's what was defined by Euler and Lagrange at the time in 200 years ago, 300 years ago, to define the principle of least time. In fact, which is equivalent to the principle of least action, and it's the underlying principle for each for all of known mechanical science, but and so you have Hamilton's principle, who defined it with action rather than time, and in fact you can derive Newton's second law, F equal to ma, for example, from the original Euler-Lagrange equation in kinematics. But we've got here a thermodynamical equation using a purposive Lagrangian, and in effect that implies actually that we must have a force that defines a force, which you might call a motivating force, and then in the cartoon here we have the key equation that the purpose, entropic purpose, is simply the line integral across complex time of the purposive integral dz, where dz is the little bit of complex time across in the time plane, and that defines the purpose of the system is the integral of the purposive Lagrangian across the complex time plane. So this is to repeat. Sorry, why are Lagrangians so important? So as just to repeat myself, it is the fundamental concept in all of physics and all of its classical mechanics, quantum mechanics, general relativity or field theory, quantum field theory. They all require a Lagrangian. In fact, they're all defined using a Lagrangian based on the principle of least action, based on the Planck constant h bar. And it's been Max Planck himself said in 1915 that the principle of least action dominates all of mechanics as well as all other physics, and even Richard Feynman 1949 said all of mechanics and electrodynamics is contained. Have you lost my slide? Sorry, I'm just losing. That just commenting that the principle of least action underpins all of known science, but that's based on the Planck constant, principle of least action. and with it you can define, well, Newton's second law and also Snell's law of refraction, and it's independent of the coordinate system. And then you can Noether's theorem start applying with the Euler-Lagrange, and you can define the conservation of energy, conservation of momentum, conservation of angular momentum, all due to the symmetries of the Lagrangian. So having a purposive Lagrangian based on Boltzmann constant is actually quite an important discovery. We think it should be very has quite very interesting, important implications. So we can define, being able to define this Euler-Lagrange equation. As I said, we can define a principle of least entropic purpose. So a system to follow the trajectory across the complex time plane, where the entropic purpose is the integral, line integral along that trajectory of the purposive Lagrangian across time, and there being a principle of least entropic purpose, then the variation delta p will be 0, and you can define that when a system evolves, so it can adopt a multiplicity, lots of different trajectories across the complex time plane, but the trajectory that it actually will adopt is the one that minimizes the purpose, which requires least purpose. And as I say, you can what is interesting is that the Lagrangian is because it's defining complex time, it has no spatial components, and that's why it's purely about time, and it's future oriented, and that's why we say it actually has purpose, because it's looking forward. It embodies the arrow of time, and it just defines how the system navigates its way through time, and you can define the motivating force for the purpose using the Euler-Lagrange equation. Here I've done it very just explicitly using the purposive Lagrangian that exists, just to show that not just, it is theoretical, but we've actually got the solution, a solution. There's multiple solutions, but we show that there exists at least one solution for which is the analytical solution for this principle of least entropic purpose. Now, what's interesting as well is using the symmetries of the complex plane, and quite sort of analogous in a sense to the idea of the energy and entropy production are isomorphic to each other. What we found was when we define the purpose as being the line integral of the Lagrangian across the complex time plane, but but if we do the same integral but using the Wick rotated complex conjugate of the purposive Hamiltonian, we get the information, and in fact we find that they're equal to each other. In fact, that the entropic purpose is equal to the information created, and this actually is quite satisfactory or satisfying in the sense that if you're thinking of conscious beings or entities that are alive, they're always making lots of strategic or tactical decisions as they go about their life to maintain life, if it's looking for food or doing things that they find interesting, and this is where we find that the purpose exactly is identically equal to the information that is created by the system or by the entity, and we came across a fascinating paper by Deacon and Garcia Valdecasas, published a couple of years ago, which actually says pretty much the same thing, entitled "The Thermodynamic Basis for Teleological Causality," in the sense that purpose can often be thought to have teleological connotations, and so that this would appear to conform to Deacon's and Garcia Valdecasa's thesis that there is a thermodynamic basis for teleological causality in the systems that they study, and it's this idea that you have this appearance of teleology, for example, well known from the principle of least action, when a ray of light exits a body of water into air and bends and is refracted to take the least time to go from A to B. What is always curious is just how does the light know which angle to refract by in order to reach its destination in the shortest time. Now, the science and the maths can explain it by saying that everything is determined, but there are still it still looks surprising when you first see it, that you have this apparent teleology occurring in a system, and there is when we look at entropic purpose, there is that aspect that is in creation of information had its own subtleties, in the sense that information is by definition acausal, non-deterministic, and unpredictable. So that if you're having a purposive system which is trying to follow a trajectory across complex time and is creating information, you can define an angle theta here, which is quite analogous to the theta, to the angle of refraction by water by a light ray coming out of water. But how does the system know in advance what angle it should adopt in traversing across a complex time plane? How does it know in advance the information that it's going to create? And for me, that's still quite an interesting little dilemma or kind of paradox, which I'm still trying to get my head around. But there is this issue that what we have here, something that is future oriented, directed, which is pointing into the future, and actually has this teleological aspect to it, which we're still trying to work out. I just wanted very briefly just to show. I've been showing you these complex Lagrangian Hamiltonian framework for purpose, and this arose out of work we were doing in quantitative geometrical thermodynamics, QGT, over the last few weeks, and one of the fascinating aspects is that we can use this thermodynamic Lagrangian Hamiltonian framework to derive the holographic principle. Now, the holographic principle is most well known, actually, in physics of a black hole, where the surface area of a black hole with its Schwarzschild radius exhibits or is equivalent to the entropy of the black hole, and because all its information is on its surface, it's called a holographic, because it's on although it's a three-dimensional volume, all its information is stored, or can be found at its two-dimensional surface, and that makes it somewhat holographic. We've used our Lagrangian Hamiltonian formulation. We published a paper in 2021 showing how you can derive the holographic principle. But what's interesting is that the holographic principle doesn't just apply to black holes; it applies universally to any system. I suppose particularly to a system which is maximum entropy. And one of the results we found, which we published in 2022, was that we could use the holographic principle and apply it to nuclei. So black hole is quite a large cosmological object at the center of a galaxy, but we can also use it to define the radius of an atomic nucleus, particularly helium and its various isotopes. And we were able to use the holographic principle, which was derived using the Lagrangian Hamiltonian formulation, to very accurately calculate the radius of these nuclei. And then we were able to go further. I've been discussing Nernst's theorem and conservation laws as applied to Lagrangian, and one of the critical ones, like that energy is conserved, but also so is entropy production, or the rate of change of entropy with time. And so we have these. We have going back to nuclei again. We can use conservation of entropy reduction, and we have the entropic or thermodynamic equivalent to the Planck-Einstein equation to calculate the half-time, the decay rates of a whole system of radioactive nuclei. And we calculate the entropy or the degrees of freedom, and we can get the same measured empirical half-lives within 1 or 2% using our Lagrangian Hamiltonian approach. So one aspect, so the Lagrangian purposive Lagrangian said, Nernst's theorem says that they ought to be conservation of information production, or indeed conservation of rate of change of purpose. And this is also another interesting line of research as to if the rate of change of purpose for a system is a conserved quantity. Well, what does that mean? And so this is a direction of research that we're wanting to go into next. So I'll just now conclude with just final remarks about our entropic purpose. So it's a future-oriented thermodynamic theory. It's based purely in time, complex time, require reversible and irreversible thermodynamic time. So it's purely temporal, and it's a unified theory in the sense that it considers systems in a unified fashion, which says it can both reversible and dissipative at the same time and in various degrees. Basing it on Shannon information and the creation of Shannon information, in just the same way that Shannon information is impersonal and measurable. Therefore, the entropic purpose, as we've defined it using Shannon information, is also an impersonal and measurable description of entropic purpose, and we've got very heavy mathematical underpinning to it, Lagrangian Hamiltonian, which allows all sorts of symmetries and mathematical insights to be exploited. And in fact, although what we found by finding that the entropic purpose is identically equivalent to the information created, that is actually quite a trivial result, but quite attractive as well. But what we've shown is that you look under the hood, and at a very complex mathematical structure framework underneath, which is underpinning that very simple identity between purpose and information. And as I said, there are lots of interesting philosophical as well as practical scientific implications and applications for this that we feel other scientists and people like yourselves will be interested to pursue. So, thank you very much. We can have questions and discussion.
I think we have some hand raised. Sripad, can you please unmute yourself and ask question directly to Michael?
Yes. So thank you very much for this insightful talk. So I have come to attend your talk mainly to understand the concepts because I'm not working exactly in this particular research line, but I have a very basic, very simple question that when we talk about an entropic purpose, how does it link to the minimization of the gradient of field variables? That is point number one. Point number two is that there are now two components which you mentioned in time, the conservative where there is no entropy production and the dissipative where entropy production takes place. Then is it not that the least action principle applied to dissipative systems is the same as maximization of the entropy production rate, and that reduces to minimization of the gradient of field variables at the fastest rate? So that is my question. And is that
Okay.
not the entropic purpose of any dissipative system?
Yeah, so let's take the last question first, because I'm already beginning to forget the earlier ones. But what is interesting is, yeah, obviously the principle of least action is still valid, but what we see here is an additional degree of freedom, I suppose. That there's an almost, let's say, at 90 degrees, just like there's complex time, real and imaginary time. So you have to have orthogonal to the principle of least action. You have the principle of least purpose, and they have to be they have to conform. They're complementary to each other, and just like, I don't know if you understand from your complex variable theory, theory. If you have an analytic function or holomorphic function, you have a real function and an imaginary function, and they define each other via the Cauchy-Riemann equations. My suspicion is that basically purpose and action all kind of relate to each other in the same way by a set of differential equations, and that they are complementary to each other and conform to each other, and agree with each other, because you have the extra degree of freedom, the extra plane, let's say, or call it the imaginary. It's not imaginary. It's just an artifact of history, because Descartes didn't believe in square root of -1. But although it's called imaginary, it's just as real as real numbers. So it's not a figment of our imagination. It actually exists, but an extra degree of freedom which needs to be taken into account. Sorry, I forgot now the first point or so, your question you were asking.
The first point was actually the link with the minimization of the gradient of field variables. So because the two, entropy increase and reduction of gradient of field variables should be the same. So I thought that entropic purpose of any dissipative system is to minimize the gradient of field variables. And as I understand, that is the basic purpose of the creation of dissipative structures of far from equilibrium. So
Yeah.
because that is another point which I thought I would like to learn from your talk. That is, how does this talk help me in trying to understand the role of dissipative structures, their emergence and their evolution?
So I mean, dissipative structures. Normally, we would tend to think of them as being noise producing, but we also understand that noise and information are intrinsically the same, in the sense to have the same physical properties of not being non-deterministic, acausal, non-predictive, non-determinative, and so and of course, living beings are all dissipative, as I'm a dissipative system, but kind of in my dissipation, I'm creating information, and that's part of my purpose. And in terms of entropic purpose, we were saying that the principle of least entropic purpose is that type of economy or efficiency of operation, is that you try to achieve your goal with a minimum amount of noise or information that you create while going about your business. And so that's the principle of least entropic purpose. So I don't know if that answers your question about dissipative systems.
Okay, thank you very much for the clarification.
Thank you.
I can see one question here in the chat. It's the question from Jing Ang. Does the purpose always come from a mind? Otherwise, how could the purpose be a purpose? I'm reading that from a chat box.
Yeah. Yes, I think this is for me. This is one of the I'd say more philosophical, speculative aspects, because for me it's still a bit of a mystery as to where the information comes from, or what creates information, as to whether a conscious mind is required to create information. So from that perspective, the question is does purpose always come from a mind? Potentially. Yes, as in just as in Shannon information always requires an intelligent being. As in Shannon information is ubiquitous around us, but it's only because it's ubiquitous, only because humans have created telecommunications networks, computers, and all sorts of other information transmitting, processing systems. Which work on Shannon information, and without these engineers, conscious engineers, we wouldn't have these systems, or indeed we wouldn't have Shannon information as such. So for me, there is a little bit of a circular loop that purpose requires information. Which requires conscious minds, and conscious minds kind of require purpose. So yes, there is a bit of a circularity there. But what I find interesting is that we can see the circularity, but we can see underlying it though is a very sophisticated mathematical framework as well, which conforms to it. So or which it conforms to, and so we've only just started. So there's still a lot of possibility for better understanding of how this circular relationship actually operates.
Thank you.
I think I saw William Sarwell. Please, William, would you mind unmuting yourself and ask question to Michael directly, please?
Yes, hi.
Hi, William.
Thank you so much. I think your work with Chris has been breathtakingly beautiful, and so broad in its applicability and so beautiful in its symmetry that I think it's a major contribution. And I'm sorry that more scientists, more physicists haven't taken notice of your work, but it is, I think it's groundbreaking. And thank you for it. I wanted to ask questions about your views around the origin of life and consciousness. You did address consciousness in the previous question. So as somebody, as a researcher who's worked on origin of life issues, I'd be interested in hearing your thoughts about that in particular.
Yeah, I mean, for me, the origin of life, if it's it all revolves around where does the information come from, and for me that's still a profound mystery, actually, in a sense. You have some people call it specified information, but there's a huge amount of information if it's within RNA or DNA, and just quite how this specified information where it comes from is still a bit of a mystery. This is what I was trying to so we can show that within the structure of a purposive Lagrangian, we can understand, yes, entropic purpose requires the creation of information, and so we have this circularity, but kind of then kind of, so origin of life requires a lot of specified information, and that's still and then the probabilities of them spontaneously appearing, for me, just don't seem to match or stack up. Then kind of you can calculate the probabilities, and they're astronomically small. And I'm still kind of interested to understand for me, as an origin of life, has to explain where the information came from.
Would you say that the inherent nature of the physics involved and in the universe, the presence of purpose in this limited sense, or even in a broader sense, almost dictates the requirement of evolution, not just of all systems, but of life in particular? It seems like it's built in, it's inherent.
Yeah, actually, you're right. Yeah, I think I'm forgetting what I said, because one of the fascinating things is this issue of hyperbolic space or hyperbolic space-time, which seems to be intrinsically informational,
Right.
which is still quite a difficult thing to think about. But perhaps that's what the answer is. The universe, in its structure, if it's hyperbolic, is intrinsically, inherently informational, and that information is trying to come out, and that's what the mathematics is telling us, which is quite a remarkable thing to say. So it's not Euclidean, it's hyperbolic, and the fact that it's hyperbolic makes it informational. If it were Euclidean, it wouldn't be informational, but if it's hyperbolic, it's informational, and that it's intrinsic and inherent to the whole fabric of space-time, and that's quite a huge thing to try to take on board and understand. So, but that's what the answer is.
Yeah. Thank you so much.
Thank you, William.
Now we have Terry here, and Terry and his students are in the room, and actually Terry suggested I invite you to the meeting. And Terry, please unmute yourself and ask directly to Michael.
All right. Well, it's great to hear the story again. I've struggled through your paper many times now, and I agree with William that it's a remarkable work. All of your work is remarkable. I, of course, am someone who studies biology, in particular evolutionary biology, and origins of life is, of course, one of my major topics as well, and in particular, the origins and nature of information. And I wanted you to talk about two things. And we use the term information and we use the term purpose in polysemitic ways. That is, we've used it at different levels. When I talk about information from Shannon's point of view, I'm not talking about something that's about anything else. To be about something is to be linked to something that it's not. Shannon does not deal with that. In fact, he sets it aside, and you've done the same thing effectively with the concept of purpose. But we also do the same thing with purpose. We can talk about end-directed processes on the one hand, and then processes that are directed towards an end that is represented. So, as I wanted to tune into this conversation, I had to do a lot of things that were represented. The future did not determine it. This moment did not determine what I'm doing in any physical sense. And this is sort of the acausal problem you're struggling with. Information, to some extent, from Shannon's point of view, that is, there's two ways that he measures information. One is, of course, the channel capacity, the entropy of the channel, but the other is the redundancy within it, and redundancy in particular with the recipient, and how the recipient can distinguish what is redundant and non-redundant with respect to an anticipation. And so that even Robert Fano, for example, struggled with this problem years ago about Shannon's notion of information. Shannon didn't, in fact, feel comfortable with calling all of what he was doing as information, because he was specifically not dealing with this relationship of aboutness, of being referential to something else, or being valuable, useful. So we think about information, if I've heard this before, it's not news, it's not useful to me. So that there's a use aspect, a pragmatic aspect to the notion of information, and a referential aspect to the notion of information. These have both been excluded from your discussion. And I think the question, if we want to talk about biology, want to talk about the kind of information that might be captured in molecules, the kind of purposiveness that might be in living things as compared to, say, helium nuclei, that they're going to be different. there's something added. And so I see the kind of work you're doing as sort of, as Shannon's was at the base of a problem that is not actually the full story. We've got to add step by step by step. My thought and my interest in one of the things that you've talked about, I think of the transition from non-life to life as the beginning of an evolutionary process, which is a process of generating novel information, novel referential information, novel aboutness, novel adaptation. And in that sense, it really fits well with your definition of entropic purpose. But of course, we don't think about the evolutionary process as purposeful in the way we think about my own actions, or even the actions of, say, a bacterium searching out food, avoiding danger. There's a different kind of purpose there. But my suspicion is that you have taken a step that's halfway there. I think about the way that evolution adds information, builds information, and constructs level upon level of information as a process that's very well captured by this notion of entropic purpose. So I may be talking too much here, but I was interested in your comments about those additional levels, that is, after we move away from and above and build on entropic purpose.
Well, yeah. So I mean, the comments you make, Terry, are fantastic. I feel, yes, what I've done. I mean, what we've done is obviously interesting, but it's very pared down. It's very minimum or de minimis almost. But you've got to start somewhere. so I'm hoping that it does form a foundation and it can be built upon. One of the interesting things, aspect about entropy or thermodynamics, or this hyperbolic or logarithmic aspect, is that it's scaleless, and you have to define your scale. So although in a sense we've defined a bottom, the base kernel of how to approach this, it seems to me that by adopting a different scale, you can build upon it, and perhaps a scale of complexity. You have the same principles, but then apply them at a different scale. Now, how those different scales interrelate, that's kind of like emergent phenomenon, is still obviously the stuff of future research. But I think built into this issue, that it's scaleless, it kind of means that there's a lot of opportunity to look at it at different scales and different levels of complexity, say, and see what happens. Who knows?
Is there any other question, comments? That's really, like William has said, it's really very interesting, and it opens up a lot of door in the direction of the research, especially research we are trying to extend to the living being. And that's really amazing. And is there any other question from the room? I don't see any hand raised, but there's a final call if you have any question. If not, let's give a big clap to Michael. That's for the great presentation. And there are lots of people in the room doing the similar research, Michael. Therefore, they might contact you later. But
yeah, wonderful. Yeah, very open.
Yeah. Thank you for accepting our invitation and this great talk. And we really appreciate your time and sharing this information to this audience. And please accept our thank you from this Thermodynamics 2.0 community. Thank you, Michael.
Thank you, Am. Thank you very much. Thank you, Eduardo, as well. It's been a pleasure, and I appreciate your questions and your interest.